if we have an account, bank account or some other type of account that's gaining interest and it's compound interest, it turns out that's an exponential function. Here's the formula. In an account with principal P, principal is just the amount you start with, that is compounded, or that has a rate R, compounded n times per year, okay, so what that means is if it's compounded 4 times per year quarterly, that means that at the end of the first quarter, interest is calculated on that, for that principal, for that amount that you have. Interest is added, and then you go to the second quarter, you take whatever you had plus the interest, and you get interest on that. So you get interest on the interest that you, not only on the amount you have, but you get it on the interest. And then the third quarter, it does that again. It gets interest on everything up to that point. So that's why it's compound interest. You're getting interest not only on the amount you start with, but on the interest that you get. Compound interest. Simple interest, you're just getting interest on what you start with. Compound interest, you get interest on the amount that you gained also. So anyway, turns out if that's the setup, then after T years, the amount in the account is this. A equals P times parentheses 1 plus R over N, close parentheses. So you take the rate divided by N, the number of times per year, compounded, and then raise that to the NT power. And that's what makes this an exponential function, because basically most of the time we're thinking the variable is the time. And so notice the time is an exponent, is in the exponent of our little formula here. But that's our compound interest formula if we're compounding n times per year. Okay? Okay, so let's take a couple of looks at an example here. All right. So how much is in an account with $5,000 that has a rate of 8%, compounded, let's do quarterly. All right, number one, after, let's say 5 years. How much is in the account? In there. So after 5 years, how much is in this account? Well, basically, this particular exercise is labeling and plugging in some numbers, right? The $5,000, that's the amount we start with, so that's our principal called P. The rate is 8%, of course, change that over to decimal. R is 8%, but in our decimal form, move it 2 places to the left, right? So it's 0.08. Then N, what is N? N is the number of times compounded per year. So if it's compounded quarterly, that's 4 times per year. So N equals 4 here. And of course, in this particular case, the time is in years, and so be careful with that. Sometimes they give it in months, so change it over to years to go in this formula. So t equals 5 here. So we've got A equals P, so it's 5,000, times 1 plus R is 0.08, divided by N, which is 4. And you raise that to the NT, so that'd be N is 4 times T is 5. That's going to be the 20th power. What I recommend is go ahead and simplify this in here. 0.08 divided by 4, that's 0.02. 1 plus 0.02, so that'd be 1.02. And then that's to the 20th power. So that's going to give us plug that in, $7,429.74.
I want to know where you're getting 8%. Not like in
8%?
I'm just joking. At the
Oh,
bank.
Okay.
That's
Oh,
a good
yeah.
interest rate.
Oh, yeah. At a, like I said, it could be at a bank, could be factoring,
Good
figuring it
luck
on
finding it
a,
nowadays.
yeah, on a stock. Your stocks might be a little better
Yeah.
exchange on that. All right. Yeah, so how much do we have after 20 years? So that'd be A equals 5,000 times 1 plus 0.08 divided by 4 again. And we're going to raise that to the 4 now times 20, so the 80th power. So it's 5,000, 1.02 to the 80th power, which gives us $24,377.20. All right, so yeah, it goes up pretty quickly. I mean, this is just putting in some money and letting it grow for 20 years compared to 5 years there. So yeah, so with the compound interest, it grows pretty nicely there, and with the better rates, of course. All right. Now, what I would say is on these, the one thing that changes, of course, is the compounding, the number of compounding. Let me just mention here without going through a whole nother problem. All right, so if it's compounded monthly, that's N changes into what? Well, there's 12 months in a year, so that'd be N equals 12. Semi-annually, semi, half, 2 years, I mean, twice a year, N equals 2, yeah. So if it says semi-annually, N equals 2. I think the way, there's different institutions do it differently, but if it says daily, I don't know if we have a daily one in the homework, but they do use the 365, N equals 365. So those are the, annually, of course, would just be N equals 1. I think those are the main ones that they have us do on these assignments here. Okay? Now, there is another formula though. So this is if you're compounding quarterly, monthly, semi-annually, daily. Well, it turns out there's a limit to this interest that you can compound, and it comes in a different formula here, and that's with continuous compounding. Yeah, so daily, that's pretty frequent compounding. And if you get daily compounding, that I'd say probably take it. But even better would be hourly, by the minute. But like I was saying, that there is a limit to this, and that's this continuous compounding. The idea is that's compounding instantaneously. And so that is the limit to the compounding you can have. Good news is the formula for it actually simplifies a little bit. The formula for continuous compounding, so if P is compounded continuously at rate R for T years. All right, so it's compounded continuously, you still got the rate R, T years. Then the amount is given by this. A equals P times E to the RT power. So it's not a long formula, I call it PERT. It's the PERT formula, P times E raised to the RT. And so your rate, turns out it's in the exponent with your time there. And the other thing is the base, on that other one, the base changes depending upon the rate and the number of compoundings, but continuous compounding, the base is E. So this is one example of the natural base where the natural base occurs. It's in this continuous compounding problem. So yeah, but it's the same, basically the same deal. If 5,000 is compounded continuously, with rate, let's go 2.5%. How much is in the account after 10 years? Let's do 12 years. After 12 years. Yeah, so the key words you're looking for here are the compounding continuously, because we have two formulas now. P times 1 plus R over N to the NT power. And then A equals PERT, P E to RT. Yeah, and so those are the key words that you clue in on that you use the PERT formula there. And so A here, we've got 5,000 is the P, right? Amount we start with. Then we have E to the RT. Well, the rate is 2.5%, and so what goes in for R there?
0.025.
Yeah, you got to move it two places back. Even though you've got a decimal there, you still got to move it two places back, so the R will be 0.025. And then the times the T, which is 12. So we just plug that in. Plug that into it there. Okay, 0.2025 times 12. So this is going to be E to the 0.3 power. Multiply those two together, you get 0.3. So it's 5,000 times E to the 0.3. So that's $6,749.29. That's it. Okay. All right. Another way we'll see this phrase, kind of the same, very same idea, is it's called exponential growth or decay. Another version where base E can be used for something that occurs naturally. It's a lot of times with population growth, whether it's bacteria population or people, figuring out population for city growth of cities or something like that, they usually grow exponentially or decline exponentially. Yeah, and you can probably guess, how do you know if it's growth or it's decay? Well, if I've got, say, a population, say the population time t is given by, let's make it 3,000 e to the 0.012 t. All right, so that's population after time t of a city after t years. Well, yeah, so this is an exponential growth model because this population will be growing. How do I know it's growing?
Because it's 3,000.
It's positive numbers.
You got positive where?
And that point.
In the exponent, yeah. Yeah, if you think about it, this is a positive exponent, and we didn't do any that had a number in front of it. We just did like e to the t or e to the x, but same idea. If you've got a positive number here, then you're talking about growth. It's because the exponential, think about the graph, it's an increasing graph, okay? So this would be an increasing graph. The shape of it would be an increasing function. And so this is growth, okay? Because of your exponent. And a lot more we can say here, but positive in the exponent. If you have the negative 3,000 e to the negative 0.005 t, that would be decay. Exponential decay. Yeah, it's really all based on that number because that tells you decreasing graph or increasing graph. That's where that's going to tell you that. So anyway, very same idea right now. Anyway, what they'd have you do. So let's say, what would the, so for this one, what would the population be in 7 years? That'll be P7, 3,000 times e to the negative 0.005 times 7, 0.35, 0.035, so it's 3,000 times e to the negative 0.035, right? Yeah, 2896.81, and so round that off to the nearest, yeah. And so that confirms there it is decreasing. Well, I know, okay, so I didn't mention that. What did this population start out at time 0?
3,000.
It'd be 3,000, right? So at time 0, t equals 0, we have 3,000 e to the negative 0.005 times 0. Well, that's going to make that 3,000 times e to the 0, right? Which is 3,000. So yeah, this number right here, that's the number you start with. The 3,000. That just like on the compounding stuff. That number is the number that you start with, or is at time 0. So anyway, any questions on that? Because I'll have some other problems on that later to come. Anything?
On the broker decay, is there an actual formula like you have on the other two? of them, or No.
It's this basic, I mean, it'd be,
Okay.
if you wanted a general formula, P of T equals 3,000 E to the RT, so it's, oh, sorry. Let's call it P0. Because that's your population at times 0. Yep. All right.